Vielen Dank für die Einladung und es ist natürlich eine große Freude, auf deiner Konferenz zu sprechen. But don't worry, I'll switch to English so that participants have the chance of actually following my talk if they choose to. So I will talk about pseudofinite omega-categorical groups, and this is joint work with Dougal McPherson. And I should say it's really very much unfinished work, and it's not that we necessarily want to finish it, but I thought if I talk about it here, maybe some other people will pick it up. So, of course, with Dougal, no. Oh. Oh. Okay. With Dougal, we have a number of results on pseudofinite groups. Maybe let me recall some of them. So, Katrin Tent. First, we showed that pseudofinite plus stable implies virtually nilpotent. Pseudofinite plus nip only implies virtually solvable. And we actually gave examples to show that they are not necessarily virtually nilpotent. Then, sorry, I have problems with this blackboard. Frank showed that pseudofinite with finite burden implies finite by abelian by finite. So it means you have an abelian part in the middle and finite index above and finite subgroup below. And because this will come up often, I'll abbreviate this to FAF. So this is about the pseudofinite side. And you see, depending on how strong you make the assumptions, you actually really get more. Then on the omega-categorical side, let me start with Bauer, Cherlin, McIntyre. So first we have omega-categorical plus stable. And that's virtually nilpotent. And and I think this is also maybe Ulrich Feldner was involved in here. But omega-categorical plus superstable again implies FAF. And so I'm collecting all these results here. Then David Evans and Frank proved omega-categorical plus super simple implies FAF. And this can also be deduced from the work of Udi and Greg, Cherlin, Ruszowski on smoothly approximable structures. So you see we have all these results showing that both pseudofinite with stability assumptions and omega-categorical with stability assumptions gives a very restricted class of groups, let's put it that way. So our question was, what happens if you mix pseudofinite and omega-categorical? Ah, yeah. One F too much. Yes. Thank you. Yes. So these are two finiteness assumptions that go in slightly different directions. The obvious examples of such groups are, of course, vector spaces over finite fields. There are other examples, but the question is, what else can you say? So the first observation is that in a pseudofinite omega-categorical structure, you cannot have the strict order property. So let me write it as a lemma. A pseudo-finite omega-categorical structure doesn't have the strict order property. And that's actually not so hard to see. Omega-categorical, if you assume you have a formula that has an infinite chain, by omega-categoricity, it would have to be dense, this ordering, at least at some part. And by pseudofiniteness, it has to be discrete, so the two things are not compatible. So no strict order property in this setting. And Dugald has an old result about omega-categorical groups without the strict order property. And they are immediately, so maybe let's put it here. This is an old theorem of Dugald's. Omega-categorical without strict order property implies that you have a characteristic nilpotent subgroup of finite index. So as a corollary, we immediately get that in the omega-categorical pseudofinite setting, then we have a nilpotent characteristic subgroup, and this nilpotent group is of finite index, and this nilpotent group is actually the direct product of the Sylow P subgroups. So we are reduced to a direct product of P groups. P has finite index nilpotent characteristic subgroup, which is direct product of its Sylows. This should go up, I think. Oh. So this is direct product of P Sylow subgroups. And of course, there are only finitely many of those. And one other thing to observe is that characteristic subgroups in omega-categorical groups are always zero definable, and if and only if any zero definable group is characteristic subgroup, and conversely. So let's look at other examples than just the vector spaces over finite fields. So the first examples that we have are the extra special groups, extra special P groups. So they are nilpotent of class 2. the center is cyclic of order p. And G mod the center is a p vector space, elementarily abelian p group. And the easiest or the smallest example of this type is the strict upper triangular matrices that we saw yesterday in Zoe's talk over Fp. So you see, this is, if you put zeros here, this is the center, and here, this is the group mod the center. It's two-dimensional. And to get extra special p groups, you can take arbitrary numbers of copies of this and take the central product over the center. So if you take infinite central products of these, you have extra special p groups, and you can see that they are actually pseudofinite and omega-categorical. So they are nice examples, non-trivial examples. Apps showed that if you generalize this, if you take a finite step, two-step nilpotent group, finite two-step nilpotent, I don't know whether you actually need p group, I don't think so. And you take a group that sits between the center and the derived group, and you take the products over k, infinite products over k, you also get omega-categorical groups. But we cannot say whether they're pseudofinite. Infinite, let's say, central products over k are omega-categorical. But we don't know whether they're pseudofinite in general. So that's one of the question marks. So, sorry? Is K what?
Contained in the center.
Yes, sorry. That's what I meant to write. Yes, thank you. We don't know whether these are examples, but we do have some other examples, namely if you, I think I can fit it here. Maybe not. So another example, if you take a symplectic form, V cross V, let's say to Fp to the n, is symplectic form. So a bilinear form given by, let's say, ones and minus ones on the off-diagonal blocks. V Fp to the n vector space. Then you can define a class 2 nilpotent you get a group class 2 nilpotent on this set with the multiplication V1A times V2B given by addition in the vector space, and in the second coordinate we take A plus B plus the result of the symplectic form. And this is easy to check that this is a class 2 nilpotent group whose center is exactly fp to the n. And if we have n equal 1, we recover the extra special groups. So the center of G is again this field, and G modulo the center is isomorphic to the vector space. So maybe it's worth recalling this bilinear form structure that we get in two-step nilpotent groups. So here's a remark. If you look at commutators and with products, the way they behave is typically not bilinear. You have to twist this by conjugating by y, and so on. This you can easily verify by writing it out. But of course, if this commutator lives in the center, then conjugating it doesn't matter. So in a two-step nilpotent group, what this says is really that this is bilinear in each of the coordinates. Sorry, I have long ways to walk. If G is two-step nilpotent, then x, y, z is equal to x, z, y, z. This means that the commutator actually induces a bilinear form. And so we keep this in mind. There is one class of nice omega-categorical groups that was defined by apps, and it generalized the results by Saraceno and Carroll. So these are the existentially closed P groups of class, nilpotent groups of class 2. Generalizing Saraceno word. Sorry. One can only move one word at a time. It's amazing. I wanted to be efficient and move all of them, but no. So, so the result says the two-step nilpotent P groups, which are existentially closed, two-step nilpotent with exponent P. This theory is complete. Omega-categorical and axiomatized by the following axioms. So of course we can say it's two-step nilpotent and exponent P. So nilpotent of class 2 and exponent P. The next thing is to say that the center is exactly the derived group and consists exactly of all the commutators. So the center is infinite and equal to set of commutators. And the last axiom is very nice. It's Alice's restaurant axiom. It says you can get anything. So we have the axiom scheme. Sigma n for each n. It says for all G linearly independent, so linearly independent viewed as a vector space over Fp, independent G1 to Gn, not in the center, so in G, not in the center, and all linearly independent H1 to Hn in the center. You can find a unique element not in the center, of course, such that the commutators of G with these elements give you H. So there is some K in G, obviously not in the center, such that you match the commutator of Gi with K gives you Hi for each. And when we were looking at examples for pseudo-finite omega-categorical, we started in a very neutral way, let's say unbiased. We didn't know what to expect. But it turns out these are not pseudo-finite, and I want to quickly show why not. We have the let me bring this down and this up. Sorry, it's very slow. Okay, so this is the axiom scheme for the group. And the lemma says the following. V, W, beta be a two-sorted structure. Beta from V cross V to W, a bilinear map. And V and W vector spaces over Fp of dimension at least 2. And yeah. Now, if you take the sentence saying, essentially expressing the first two axioms here, for all linearly independent V1 and V2 in V, and W1, W2 in W. There is some Z such that beta Vi Z is equal to Wi. So you can see that using this interpretation as a bilinear form, this is exactly the sigma 1 and sigma 2 expressed here. And the statement is that this sentence, Thai has no finite model. And of course, that then implies that these examples by apps are not pseudofinite. So why doesn't it have a finite model? It's actually just by counting. So let me give you the proof. For any fixed first coordinate, we get a linear map. So let's fix the dimension. Dimension of V equal n, dimension of W equal D. And then by this axiom, if we fix any non-trivial element in V, the map beta V of X is beta of V and X is surjective, right? This is in particular for any V1 and any W1 you can find such a thing, so it's surjective. So immediately we know that n is at least D. And the kernel of this map has to have codimension D. So let's call this dV is the kernel of beta V has codimension D. Okay, so that's one observation. Now, what this is saying is that the pre-image for any W1 and the pre-image for any W2 intersect, because you can find one that lies in the pre-image for both of them, which is exactly saying, and pre-images, of course, are cosets of kernels. We all know that from linear algebra 1. So it's useful. So pre-images are cosets. Cosets of the DVs, I mean, of these sets. So pre-images have to intersect, hence all for, if we take for V1 different from V2 and A and B in V, we see that dV1 plus A, so this coset will intersect this coset, non-trivially. Right? That's exactly the statement that non-empty. Thank you. Yes, it's exactly the statement that you find a common pre-image for both of them. But now it's easy to compute that if you have subspaces with this property, then their sum is the whole vector space. Of course, you need that V1 and V2 are linearly independent, because clearly, if you take a multiple here, the kernel will not change. Okay, so now we dualize and look at the dual space. Consider V star, the dual space. And we have the corresponding dual subspaces. And now, instead of saying that they generate everything, they have dimension D. Before they had codimension D, now the dual has dimension D. And they don't generate the whole space anymore, but they intersect trivially. And this happens whenever V1 and V2 are linearly independent. V1, V2. Now, how many linearly independent vectors do we have? Well, this vector space has dimension n, so we have, I think it works fine to just push it. So we have irritates. Okay. Okay. It's hard not to do it. So this is the number of linearly independent vectors that we have, obviously. The vector spaces have dimension D, at least 2. So now we are claiming that we have this number many subspaces of dimension D that intersect trivially. But this is the number of vectors that we have. So impossible to make them into, to group them into that many subspaces that intersect trivially. Many such subspaces, and that's impossible, right? Because if each of these vector spaces has dimension greater than 2, well, you need more than that many vectors to make them disjoint. Okay, so this sentence doesn't have a finite model, and that again implies that what I said before, that these existentially closed groups are not pseudofinite. Okay, so as a corollary, these examples by apps are not pseudofinite. Yeah?
I think I'm missing something. So you're using the property, this linearly, this property to get the surjectivity of the maps beta Vx,
Yes.
right? But there you only would need it for one element, not for a
Yes,
pair.
yes, yes.
But where are you using it for the pair?
That's exactly that they have to, that the cosets intersect non-trivially. It means any two given VIs give you a linear map with certain, and the pre-images of these linear maps for any given element are of the form that I wrote down, are of the form kernel plus some element that is mapped to that.
Okay, thank you.
So I'm glad to explain this. Yes, so basic linear algebra.
Yeah.
It's surprising to be so useful here. But okay, so it's a direct corollary. These groups are not pseudo-finite. And then it turns out we checked the Baudisch, Andreas Baudisch had some construction of two-step nilpotent group where he amalgamated Lie algebras in a certain way. And they also satisfy these sigma 1 and sigma 2, you can see from the things. So Baudisch's groups, I don't want to get into exactly what they are. Baudisch's two-step nilpotent groups are finite by abelian, but not pseudo-finite. So what you see here, and they are omega-categorical. So being finite by abelian is not enough for an omega-categorical group to be pseudo-finite. So that's just a side remark. And when we reach this point, I kind of talked Dugald into conjecturing that all pseudo-finite nilpotent groups are FAF. So if it's wrong, it's my mistake to phrase it as a conjecture, but Dugald thought it should be a question, but I thought conjecture sounds maybe more attractive for young people to prove us wrong or to prove the conjecture. So that's our conjecture. Let me write it down. Every pseudo-finite omega-categorical group is FAF. And to be more precisely, has a characteristic two-step nilpotent subgroup. Has a characteristic two-step nilpotent subgroup of finite index, characteristic, not open, sorry, subgroup of finite index. And then this nilpotent group has finite derived group. So because it's finite and the group has no proper characteristic subgroups with finite central derived group. Finite and central derived subgroup. Okay, so a very strong form of FAF. Why did we conjecture that? Well, there was some point we started trying to construct other examples of pseudo-finite omega-categorical groups, and we had some relations, and this looks like it could be a possible example with an infinite center. And then, well, an old colleague of mine, Bettina Eick, is working on algorithmic problems on P groups, so she was the right person to ask. I sent her this information and she came back saying this is just an extra special group. So despite it looked very different, it was just an extra special group, so no success. And then while we were discussing with her what the options were, we started aiming for this. And so what our result now says, and that's actually the best we could do at this place, is the following theorem. Namely, our conjecture holds if it holds for pseudofinite omega-categorical two-step nilpotent two groups. So the conjecture holds if it holds for every omega-categorical pseudofinite two-step nilpotent P group. Okay, so that's the best we could do. And to prove that, we also needed help from another group theorist. Namely, we have the following lemma, which is due to Laurent Bartholdi. If you take a three-step nilpotent group, not necessarily finite, with lower central series so this is the lower central series, so gamma 3 is contained in the center. And suppose that this middle quotient is finite, such that the middle quotient, so gamma 2, is finite. Is finite, so we're assuming it's a P group, so the order is some power of m. Then we can conclude that gamma 3 is also finite. Is bound, gamma 3 of G is bounded by P to the 2m cubed. So in particular, such a group is finite by abelian. And this is really just a clever computation with commutators. So it was very useful. Kind of commissioned for this purpose here. And now I can show you how this implies, how we can use this to prove our result. Let's see, this. Sorry? Yes? Okay. Sorry? Yeah, I know, but okay. I thought in Switzerland they can even have a Y at the end. I thought he's Swiss. He's French speaking, but he's Swiss, definitely. Wow, I mean, that's. No. He's Swiss.
I know he's Swiss.
Okay, so I can use the remaining 3 minutes or 4 minutes to give you the proof. I think it's almost obvious now. So now for the proof of the theorem, we now assume every two-step nilpotent group is of the right form. Omega-categorical pseudofinite group has finite derived subgroup. And now assume that we have a counterexample to our conjecture. And we may assume that because in the omega-categorical setting you only have finitely many characteristic subgroups, so we can assume that it has no finite index characteristic subgroups and no finite characteristic subgroups. No finite index characteristic subgroup, no finite characteristic subgroup, and of minimal nilpotency class. Minimal nilpotency class. So obviously it couldn't be, so what we want to show is that such a group, after we chop off the top and the bottom, it has to be abelian, right? So we are assuming every two-step nilpotent group is not a counterexample, so the counterexample must have class at least 3. So consider the lower central series. We already know it has a finite index nilpotent subgroup. And we know that this is a direct product of, sorry, I forgot to say that because time is running out. We already know it has a finite index nilpotent subgroup, which is a direct product of P groups. So it suffices to consider P groups. Counterexample of and P group. We can assume that. And now you see the proof coming. So it goes down to some class K, and then down to 1. And of course, if you chop off the lowest part of the central series, you have lower class. Then G mod gamma K of G has lower class. still a P group, omega-categorical, pseudofinite, everything's still fine. By assumption on the minimality and two-step nilpotent, this must be a two-step nilpotent with finite derived subgroup. So is two-step nilpotent with finite derived subgroup. And now the lemma by Laurent tells us that then the bottom part here is also finite, but we assume that there is no finite characteristic subgroup, so that's a contradiction. So this contradicts the lemma. And so what's left is to show that any two-step nilpotent omega-categorical pseudofinite P group has finite derived subgroup. And I want to point out, so this counting argument for the, sorry, I think I erased it. Yeah, too bad. The counting argument that we use to show that these groups are not pseudofinite. I mean, the counting argument was greatly failing because there is no way to have so many disjoint or complementary subspaces. So a much weaker form from sigma 1, 2 would be totally enough to do that. I mean, sigma 1 is quite natural, that the derived, I mean, it's the derived group. But sigma 2 is not so natural, but you need much, much less. So as soon as you have enough surjectivity in this form, you already get a contradiction. But on the other hand, and that's another point of our paper, to collect all the different strands of omega-categorical nilpotent groups that were created over the decades. So maybe it can serve as a reference, but certainly there are too many classes to just go through the classes and check one by one, because there's no classification. But maybe such an approach, such a counting approach can give this. Or a counterexample would also be nice. So, thank you.
Okay, so do we have quick comments or questions?
Katrin, can you limit the exponent in the theorem?
Can I limit what?
Can you bound the exponent in the hypothesis of the theorem? Say, for instance, the conjecture all linear
no,
with
we
exponent
haven't.
P.
No, we cannot, because there are these examples with the simply. No, that's wet. I don't know. I mean, at least it's. It's not necessarily P because there are extra special groups, which are examples where the exponent is not P. But other than that, I don't know.
And is there something special for P equal to?
Yes, I mean, yes, there is, because the bilinear forms and the extra special groups are a little bit different. I should have said odd prime, just to be safe, yeah.
Thank you.
More comments or questions? So let us thank Katrin again.